Hi guys, this tutorial is about energy. Energy is the next subject we're studying in our physics unit. It has a simple definition. Energy is the ability to cause changes in matter. So anytime some change is happening to matter, you have energy. So for example, these fan blades are whirring around in a circle because of energy. This piece of wood is turning to ash because of energy. The water in this pot is going from a liquid to a gas because of energy. And this cheetah is going from point A to point B because of energy. Like most things in science, it's helpful to break things into categories. So just like we named forces and put them into different categories, we're going to do the same thing with energy. So there are two main categories of energy: kinetic and potential. Kinetic energy is the energy that's obvious, that we see all around us. We call it the energy of moving things or of motion. Anytime something's moving, we say that it has kinetic energy. And the something can be something that you can see with the naked eye, something large, an object, for example. Or it could be things that you don't normally see with the naked eye, things like atoms and molecules. And we give them different names depending on what exactly is moving. So for example, we refer to moving objects as having mechanical kinetic energy. Another type of kinetic energy is called heat energy, and you might think you know what that is, but actually, surprisingly, heat is something that is due to the motion of atoms and molecules and the way that they're always moving around you. You may not realize it, but the temperature that you sense of objects around you or the air around you is really due to millions of collisions per second between the atoms either in the air or in any objects that are touching your skin. And your skin detects that motion as heat or the lack of heat. All of the atoms and molecules in the universe have been in motion ever since the Big Bang. We don't know what caused the Big Bang, we just know that there seems to have been one that set everything in motion. And so even though things may look like they're not moving to you, like solid objects just appear to be staying perfectly still, the motion that they have is in all that empty space inside the atom, there's a lot of shaking going on, and you just can't detect it with your eyes, but you can feel it. Anytime you feel heat of any kind, you're detecting the motion of molecules. Another form of kinetic energy that we don't really realize is motion is sound. Sound is also moving molecules. It's molecules that are vibrating in a particular way that your ear can sense. So we say that sound is vibrational energy of molecules. So heat and sound are actually kind of related to each other. Another form of kinetic energy, electricity. What's moving in electricity? Not surprisingly, electrons are. If you get a bunch of electrons to move in a straight line, they form a current, and we refer to that as electricity. And this one gets a lot of people: light. Light is a form of kinetic energy. Light is moving. I'm sure you've heard that it moves at the speed of light. But what exactly is it that's moving in light? Well, we can say that light, it acts like a wave, but it also acts sometimes like packets of energy, and we refer to the packets of energy that make up light as photons. And this is where words like photography and photosynthesis come from, because photo is the Greek word for light. So a photon is a packet of energy in a beam of light. And those are the basic forms of kinetic energy. So anytime something's moving, it has kinetic energy. The something can be something you can see with your naked eyes, or it could be molecules or atoms or photons that are moving. But sometimes energy is not the energy of motion. Sometimes it hides a little bit, and when it does that, we refer to it as potential energy. Potential energy is stored energy. And if you're wondering how can energy be stored, well, there's a lot of different ways that it can be stored. One way to store up energy is to take something above the surface of the earth, to raise it up above the ground. And when you do that, you store up energy. And the higher up you move it away from the center of the earth, the more energy you're storing in it. And that's referred to as gravitational potential energy. And you just know this instinctively, that the higher up you bring something, the more that it has the ability to cause changes in matter when you finally release it. Right? That's what energy is, a change in matter. So the higher you let something fall from, the more energy it lets out as it falls, right? The more motion you get out of it. So gravitational potential energy is energy that's stored where? In your position above the ground. We can also store energy between atoms or molecules. When atoms bond with each other, they form substances. And if you break those substances apart with a chemical reaction, you'll release the energy that was stored in their bonds. We refer to this as chemical energy. It's potential energy, and it's the energy that's stored in food or fuels. And how do we get that energy out? Well, we actually burn the food or the fuel. So food is a type of fuel that we use in our bodies, and we do actually burn it. We burn sugar in our cells. Not all atoms that are bonded to each other store a lot of energy. They all store some, but certain chemicals have more energy stored in them than others, which is why wood makes a pretty good fuel, but paper not so much. Paper burns quickly, but you don't get a lot of energy out of it. Gasoline burns not only quickly, but really hot, so you get a lot of energy out of it. However, there are alcohols, like the ones that we use in our alcohol burners, aren't as efficient. They don't burn as hot, so you don't get as much energy when you burn them. Chemical energy is stored between atoms that are bonded to each other, and that involves just their outer electrons, just those little tiny pieces of the atom that are way out in the outer reaches. The nucleus of an atom is not, generally speaking, involved in this kind of bond. The nucleus, therefore, has energy stored in it, but it's much harder to get anything out of it. You may have heard of splitting the atom, or other ways of getting at the energy that's stored inside of the nucleus of an atom. It's not easy to do, and that's a good thing because there's a ton of energy stored in there, and we really don't want to release it unless we're prepared for it. So nuclear energy is the energy that's stored in the nucleus. And you might remember briefly talking about the strong force. That's the force in the nucleus of an atom that actually stores up this energy by holding protons together. Protons are positively charged parts of an atom, and they shouldn't be able to be near each other. They're only able to do so because of this weird force called the strong force. If you can manage to get those two protons apart, wow, do you get a lot of energy out. You've probably also noticed that you can store up energy with something called elastic, right? So we do this by compressing or sometimes by stretching. So for example, if you have a spring and you press it down, you can feel the energy building up, and when you release it, it'll push your hand back up. Or if you have a rubber band and you stretch that rubber band with your hand, you can feel the energy trying to snap it back together. And then finally, you can also have potential electrical energy. This is the kind of energy that's stored in, say, a battery. What a battery does is it separates a positive and a negative charge from themselves, so that once you make a connection with a wire, the negative charge, the electrons, can move towards the positive charge. But until you actually connect the two ends of the battery to a circuit, that won't happen. And so it's temporarily stored until you actually hook it up to create a current. And finally, there's a law of energy called the law of conservation of energy, which I've written right here. The law of conservation of energy says that energy cannot be created or destroyed. It can only change forms. So energy is constantly changing from kinetic to potential and potential to kinetic and back again. Sometimes it's mechanical energy of motion, sometimes it's heat, sometimes it's in the form of chemical energy, and it's always being transferred around and moving around, so it often seems to the human eye like energy is being lost. And in fact, you'll hear humans always saying that we want to conserve energy, we have to worry, we don't want to waste energy. But in reality, the universe has a certain amount of energy in it. We can't really waste it. It can disappear from a place that's useful to us, but that doesn't mean it's gone from the universe. So for example, if I have a car driving over the surface of a road, you might feel like, well, eventually you're going to use up all of the fuel, all of that chemical energy in the gas tank. And that's true. But that chemical energy will be converted into heat and light. There'll actually be burning going on in the engine. And that burning will result in the release of heat and the release of light. And it'll also create motion, mechanical motion for the wheels of the car. And that mechanical motion will in turn create friction with the surface of the road, which will create heat and sound. So energy is constantly changing forms and constantly dissipating out from where it started into the surroundings. To dissipate means to move away from the center and move outwards and get less and less. So it seems to us a lot of times like energy is disappearing, like you open a window and all of the heat goes out of the room. Well, the heat does move, right? The molecules, the moving molecules do bump into each other and escape into the colder air, but that heat energy isn't gone from the universe, it's just gone from the room. So this brings us to the energy lab. In this lab, you have two tasks. First of all, you need to change some variables in this roller coaster that I have drawn down here. Actually, it's a picture of a roller coaster. And you're going to set one up just like this using the same materials I did. I used foam insulation tubing for the first part and a little bit of Hot Wheels track for the second part. And you're going to change some variables on this coaster. You have to keep the loop and the hill so that you lose as little energy as possible in the system. And what you want is for your marble to consistently reach the end of your track, which is actually going to be way over here on the other side of the room, like over there. You want that marble to reach the end of the track with the highest possible average speed. So to do this, you need to figure out what are the factors that are affecting the dissipation or loss of energy. Keeping in mind, of course, the law of conservation of energy, which says quite clearly, as I pointed out a second ago, you can't really lose energy. You can lose it from the system, but you can't lose it from the universe. Our system is this roller coaster. So where in the system is energy being converted into something other than the mechanical energy of the marble rolling down? And that's really going to be your upcoming task. And your archive tonight should be about this question. Start thinking, start brainstorming, write, a short paragraph. Start thinking about what could possibly be ways that you could reduce the amount of energy that gets dissipated in your system. How can you prevent that marble from losing as much energy as possible so that it maintains its speed the whole way through? Come back to this slide in order to write that archive if you need to, but go on with me. I want to add one more thing. The last thing I want to bring up before we go into this lab is that we're going to be using these three formulas, which look scary and everything, but they're really very simple. I'm going to start with the one on the bottom. DE stands for dissipated energy, and dissipated energy is what we're interested in. We want to know how much energy is being lost as that marble rolls down the track. To find that out, we're going to figure out if there's any difference between the amount of energy we started with, our potential energy, and the amount of energy we actually got out in the form of motion, our kinetic energy. In theory, they should be equal to each other, but they never are, because in reality, you always lose some of the energy in the motion of an object is always lost to friction, heat and light and sound, or something happens so that you don't get all the energy out that you started with. So where does the potential energy in this roller coaster system come from? Well, that potential energy is going to come from the height above the ground. And if we multiply the height in meters times the acceleration due to gravity, that's that 9.8 number, times the mass of our marble, that'll tell us how much energy our marble should have when it's dropped from that height. Kinetic energy of the marble we can find by taking the mass of the marble again, taking half of it first, and then multiplying it times the velocity that our marble reaches squared. Because if you think about it, kinetic energy is the energy of motion, so it makes sense that a formula for kinetic energy would include something about velocity in it. So as complicated sounding as these formulas are, they're really actually very easy. I will always give them to you. I will help you practice plugging the numbers in until they start to make sense to you. But they're actually very simple, and we're going to use them to collect and understand our data from the Energy Lab. Until then, see you guys in class.